Aloha, Richard Halverson here. This is ITS148, and today is January 23rd. No, sorry, February 23rd. This is about the 7th recording. And see, let me share my screen. Okay, let me also see if I can do this. No, there's got to be more people, I guess, for me to pin myself. But anyway, so we are in chapter 4. Well, we're supposed to be in chapter 15 today, so sorting algorithms. But I didn't finish chapter 14 last week, so that's why we have two class sessions this week. If you looked at my schedule, I'm also gonna I'm gonna start chapter 15 later this afternoon because I want to sort of stay on schedule. This is actually, pretty hardcore computer sciencey type programming stuff, which everybody in your second semester of programming, wherever you're learning programming at a college, should be learning this recursion and sorting and so on. So I want to make sure I cover it well. I really like the way this book is covering recursion and the tools, the browser tools for running programs and this little mini integrated development environment is really helpful for seeing how these algorithms work. All right, so so if we look at our textbook, we are in chapter 14, and we did 1, 2, 3, 4, and so I'd like to start. I'd like to quickly review this debugging a program. So, I just used this a little bit earlier today, and it's really a clever way of really seeing where you are when you're trying to debug a recursive program. And basically, it's simple. I'm not going to go through this program, but I'll just what happens is each time recursive program calls itself, right? So this is going to be the recursive program, and where are we calling itself? Let's find it in here. Here we're calling itself, and here we're calling itself. Okay, these other cases are terminating cases. So here what we do is we pass this variable called indent. An indent is just 3 spaces. Okay, when we first call it, it's got we pass this variable here, this argument, which is going to be named indent, and it's just 3 spaces. And then each time we call ourselves again, we basically take what we have and we add 3 spaces onto it, and then we can sprinkle in these print statements. Okay, so we sprinkle in these, and this debugging a program, you always do this. You always sprinkle in print statements just so you can see what the values of the variables are as the program is executing, to confirm they are what you think you are, confirm what you think they are. And so here, by adding this indenting thing, we see that when these things run, here we're printing out the range. We're declaring what the range is. Here we're looks like we're doing a binary search or something. This is the range, and then this high and low, and then we also print out. We print out if we found the person, print out if we didn't find the person, print out if we're going to call ourselves again by searching the lower half of what we brought in with, and this is calling ourselves again. See, so when this thing prints out, these are the indents, and then so the first time we do here, and then searching upper half, that's calling itself again. That would be right here, and we call us again with indenting 3 more, and then so that's why this thing comes out 3 spaces in, and then here we're calling ourselves again, and then we get 3 more spaces, and then we end up with person not found, which is either here, or we end up with person found, which is here. And then once that happens, we end up, once this is done, once this is done and this is executed, then what's next? We drop out of the if statement, which is here. And all this does is print something out and return. Okay, so if we end up in this if, we will return. We're not going to call ourselves again. If we end up in this if, we're going to return. We're not going to call ourselves again. It's only if we end up in this else case where we are going to call ourselves again. So anyway, and what I was going to point out is that when we come down to here, when we get to here, then we are returning, we're popping. That means we're going to return, and we're going to end up at the statement just after this. We're going to end up at the statement just after this statement. Well, what statement is that? Well, that's this statement. And then we return, and we're going to end up, right after the statement that called us. And so each time we call ourselves, we're either going to be calling ourselves here or we're going to be calling ourselves here. You see. And then once we're done calling ourselves, we just return back again. So anyway, that was a little bit of a complicated explanation, but I wanted to point out those print statements. Okay, now creating a recursive function. When I was learning programming and learning how to write these things, it's just kind of like, you just sort of scratch your head and you try stuff and you try stuff. And this is a very clear explanation of what you have to do. Okay, you have to do two things. There has to be a base case, and a base case is where you're just returning a value without calling yourself. Okay, so somewhere in there's got to be a base case, and then then that stops the recursion. Okay, so it stops the recursion, just does something like print out or return a value or do things, and then it returns, and it returns to the next statement after the statement was that called it. So okay, so you write the base case, and then you have to write the recursive case, and the recursive case is the case that calls itself. And when you're calling yourself, you have to make sure that the parameter that the parameters that you pass, or the arguments that you use to call yourself, are such that you're going to eventually make your way to the base case. So you'll see how that works. So here's an illustration of factorial. Now factorial, okay, factorial is simple because it's just and, or what's n factorial? It's 5. What's 5 factorial? Well, it's 5 times 4 times 3 times 2 times 1. Okay, what's 10 factorial? 10 times 9 times 8. So now it turns out that by the way it's defined, what's 10 factorial? Well, it's 10 times 9 factorial. What's 3 factorial? Well, it's 3 times 2 factorial, because 3 factorial is 3 times 2 times 1, and 2 factorial is just 2 times 1. You see, so for each bigger number, if we're going to compute the factorial of the next smaller number is within it. So it lends itself. It's easy to use to explain. This is an easy function. It's not easy. It's a simple function that can be used to explain factorial, and you could even say it's more easily explained as a recursive function than it is just an iterative function. Of course, an iterative version would be, for n down to 1, you do, you start a variable, starting at 1, and then each time you multiply n as n goes down to 1, and you end up, in the end, you end up with n factorial. So it's the simplest algorithm for figuring out factorial would be just an iterative algorithm. But in this case, we're going to show you the recursive version just to help you understand recursion better. Okay, so here if with factorial, it's basically when n is 1, or 1 factorial is 1, and also it's, I think 0 factorial is defined as 1 also. Is that in here? Okay, so the base case. Okay, so we're writing this function here, and there's going to be the base case, and that is when n is equal to 0, and see, n is a parameter that comes in, and if n is 0 or 1, then we just return, the return value is 1. Okay. Otherwise, if it's not 0 or 1, then we're going to call ourselves. That's what we're calling ourselves. But we're going to call ourselves with an argument of n minus 1. So if this comes in as 10, okay, this fails, then the factorial value that we return is 10 times 9 factorial. If we put it, this is, it's n minus 1 is 9, so it's 9 factorial. And so you see, we're going to keep, okay, and then once this has been calculated, once this has a return value, which if n is 10, it will be 9 factorial, then we take the 9 and multiply it by the 10, and that's what fact is equal to, and then we return fact, and we're done. So once this is executed, then we return. Once this is executed, then this is executed, which stores the value there, and we return. Okay, so in both cases we return, and we see that this thing is going to eventually, each time it's decremented by 1, and we're going to finally find our way down to 1, and then so anyway, so that's an example of this here. We see there's the base case. First we do the base case, and then we do the recursive case. All right, I stared at this for 5 minutes. I'm not sure what this is trying to express, but that's okay. Okay, now this is good. A common error is not to cover all the possible base cases. Okay. Another common error is to write a recursive function that doesn't always reach the base case. Okay, so and in each case you can end up with infinite recursion. And with infinite recursion, the program fails for a different reason than an infinite loop. In infinite loop, the program fails because the processor starts running, and the operating system is saying gives each process a certain amount of time before it's going to intervene, and that time is usually like way beyond what you would ever need, but eventually that time is hit, and the processor, the operating system is able to interrupt the program that's running and spew out the error. For recursion, if you have infinite recursion, that means you keep calling a program, you keep calling programs, you keep calling methods, you keep calling and calling and calling and calling. Each time you call a method, there's something called an activation record, which stores the individual local variables that are going to be used in that method call, and it could just be the parameters that come in, but you get into this continuous call, and then finally you run out of memory. So it's the operating system says, whoa, this thing has reached its limit for how much memory I'm going to allocate, and then it interrupts, it stops, prints out the error message. So so here's a challenge activity. Did I do it already, or is this the okay, I guess I could. Okay, all right. So here we're learning about writing the base case. So in this little dumb recursive program, we're gonna write a program where we're gonna have a penny. So we start out with 1 penny, and we're gonna double the number of pennies that we have each day until we've reached the maximum number of days. So the input is the amount that we're gonna compound, or in this case it's 1 cent, and we're going to do it for 10 days. And so it's going to end up being, you know, starting value multiplied by itself, because you keep on doubling it, times 2 times 2 times 2 until you've reached the 10th day. Okay, so this is the program, and we're supposed to write the base case here. So it starts out where you read the starting pennies, you read the user days. So that's these two numbers. And then you print out the number of pennies after, and then it prints out the user days. And then it prints out this word. It prints out this all the way to here, all the way to there. And then it goes off, and then stops printing. Then it goes off and calls this recursive program and does its thing. And then when it's all done, when it's the final return of a value here, it prints that out, and that's when this prints. So what's the base case? Well, each time we call double pennies, notice we're doing it for us. We reduce the number of days by 1. So that's the days counter. So the first time we call it, the days counter is going to be 10. I don't know, whatever this is, 10. And then it comes in here, and this is 10. And then we're going to call itself again, but this time we're going to call it with 9. And then we're going to call it with 8 and 7 and 6, all the way down to if num days equals, now it's either going to be 0 or 1. Say I'm going to start with 0, see if that's the right answer. If the number of days is equal to 0, then return num pennies, because we're done. Just return this. We aren't going to do anything with it. We aren't going to double it. Not going to do anything. By the way, the doubling goes on right here. The doubling goes on when you call double pennies again. See, it goes in doubled. So this thing comes in doubled already. So we've already done the doubling. And all right. No, I'm doing this wrong. This should be total pennies equals num pennies. Because this is what we are returning. Okay, well, I'm going to see if this is the right answer. I did this earlier. I don't remember if this is the right answer. Gung. Oh, what did I do? Return. Oh. Oh, no. I want to, no, I don't return. I set it. All the returns happen here. This is good, because it's good that all the returns happen here, because then you kind of know this is the exit point. And every time we enter, we have to exit. The trouble is when we enter, before we exit, we might call ourselves again, and we call ourselves, and then we return until we're back to the one we called originally. Anyway, let's see if this works. All right, looks like it worked. Now I'm gonna see what happens if I do this. I'm gonna see what happens if I put a 1 here, because that could be a wrong answer. Yeah, right. It's off by, look, it didn't double. After 10 days, that's 512, and 512 times 2 is 1024. So it didn't double. Yeah, okay, so we missed. Okay, all right, so it should be 0. Okay, so anyway, what's next? Oh, this one, recursive function. Now here we write the recursive case. All right, so this is a factorial one. So it's 5 factorial is equal to 5 times 4 factorial. All right, so and there's the case of 0 factorial equals 1 and 1 factorial equals 1. So here we read in a value and we're supposed to write out what the factorial is. So we say that the value, which is the value factorial, is equal to, and then we go off and we compute the dang thing and we end up with a value that's printed. Now this is user val. The reason is because the first time we're actually sending in a starting, the first time we're sending in a counter, and the second time we're sending in a value. Well, it turns out that they're the same because we're going to send in 5, and we want it to count 5 times, and 5 is a number we're going to multiply there. I guess it's 5 minus 1 time. So 5 factorial is 5 times, calling it 5 more times, I guess. Or okay, so anyway, that's why those two are the same. Okay, so we just have to write the recursive part. So if factorial, if it's a counter. So if we count it down to 0, we return 1. That's because it's this case. But otherwise, we shouldn't get down there because we end up. This is the terminating case for all factorial numbers 1 or higher. So this is the actual thing that's printed out. It's the output string that's returned. So okay, so the recursive case is the output string is this number. Okay, so what's printing out is this 5 asterisk. This is 5 asterisk. So 5 asterisk, and then 4 asterisk, and then 3 asterisk, and 2 asterisk. And then in the one case, it doesn't print out an asterisk, it prints out an equal sign, and then the value that came in here. So it's so it prints out that it's going to decrement the fact counter. It's going to decrement this by 1 because it's going to, and then it's going to do the actual multiplication. It's going to take this value and multiply it by this. So this is going to be 4. This is going to be 4 factorial, whatever this is, and then this is going to multiply it. This is the last case. It's going to multiply it by the 5, and then the next value is what is let's see, the 5. Well, okay, so output string is must be factorial string next counter value next. Okay, so each time you're okay, so this puts this on there, and then in case we create this one huge output string, and we keep on returning the output string, and so what's returned is a big huge string, which is what's returned with this call. So that's what's printed. So so it's at the very, this thing prints this, and then this thing here prints this whole thing. So anyway, I think that's the answer, because this is just going to be one number that's no, okay, so well, this prints this, and then this prints all this. So anyway, let's see if this is right. Wow, looks like it's right. Okay, math functions. Okay, this is a this is kind of an interesting. Greatest common divisor, the depth of the recursion. Recursive exploration. I suppose. Okay. Okay, so recursive math functions. So they can be used to solve certain math problems like computing the Fibonacci sequence. The Fibonacci sequence is 0, 1, 1, and it's basically, it's just the first two numbers are 0 and 1. And then after that, it's you add the last two numbers and you get the next, adding the last two numbers gets the next number. So this number is result of 1 plus 0. This number is the result of the last two, which is 1 plus 1. This number is a result of the last two, which is 2 plus 1. This number is a result of the last two, which is 3 plus 2, and so on. Okay, so that's the Fibonacci sequence. The pattern is to compute the next number by adding the two previous numbers. And you start out with 0 and 1. Okay, so here's this program. Below is a program that outputs the Fibonacci sequence step by step for a user entered number of steps. Okay, so the user is going to enter how many steps would you like. So if you say I want to do 5 steps, okay, this is going to be 1 step, 2 steps, 3, 4, 5. So after 5 steps, it's going to be 8, I think. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. After 10 steps, it's 89, which is why, okay, that's the final value. Okay, and as you see, it's 0 plus 1 is 1, and then it's like this one goes there, and this one goes there, and this one goes, and so on. So you can see the pattern. Printing this out, comes in. This is the recursive program, and the way it works is it's going to print these are the two numbers. And then it calls itself again by adding, okay, so this is where the actual addition takes place. Wait a second. Okay, this ends up coming in. Okay, so you can see that V1 and V2, and then V2 becomes the first one, and V1 plus V2 becomes the second one. It comes in. So this becomes the new V2, which is this, and this is the, okay, so kind of confusing, but anyway, each time we call the Fibonacci number, run count is decremented by 1. So each time this thing comes in, run count is decremented by 1, and eventually this case is going to hit, because run count is going to be less than or equal to 1. Eventually it's going to hit this case, and when it hits that case, it's going to do nothing. It's just going to return. So returning means we're done, because we come down here, we're done. So we return, and so we return to the program that called it. Okay, we return to the program that called it. So that's going to be either we're going to return to this one, which will be done. This will be done. It's going, and then the next one after that is the program's over, or it's going to be this one. It's going to be done. But if it's this one, it's done. Then we return. So once we start returning, we're going to keep on returning. Boop, 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 boop. And each time we return, we don't do anything. So these are all printed out on the way in. They're all printed out here, and then it's called again, and then it's called for the one last time, and it starts returning, and it just returns down here. This thing and this thing. This execution is what what prints out all of these. And each subsequent execution prints out all the ones that are below it. So anyway, so that's the Fibonacci sequence. So now we're going to write a program that outputs the nth Fibonacci number, where n is the user entered number. Okay, so instead of printing out this, we want to read in this and print out this. Okay, so basically we're going to skip all the steps that prints stuff out. So it's going to be similar to this. Let's see. What did I do with the program? Let me where's my other editor? This is, okay, I want to, so I'm going to take this, I'm going to copy this, and I'm going to start fresh, paste. So this is my test.py in my ITS148 folder on my desktop in my Windows machine. Okay, so that's my my DOS prompt, or my DOS prompt here. It's in my users Rich H desktop ITS148 test UI. So user, okay, so I can run my program from in here. Okay, and you should set that up on your computer too. So let's put this down. So let's write down here. We're going to have something like well, we're going to have a num equals 5 or something. What am I going to call it? N is a user entered number. N equals 4, and then I want to n equals 4, and I want to say f for Fibonacci equals compute nth fib of n, and print f, right? Something like that. And this, okay, so the base case is if it's Fibonacci is 0. The first one is 0 returns 0 and 1 returns 1. So I'm going to do this over here on me. So base case, if num equals 0, then I want to return, let's see, I'm going to have a variable called RET. Okay, I'm going to have, because I want all the returns to happen at the end, just for clarity. Oops. And I'm going to say return RET equals 0, whatever. So if num is equal to 0, then I'm going to say RET equals 0. And down at the end here, down here at the end, I'm going to return RET. Okay, so this function will always terminate at this point here. You know, it'll do whatever case it is and then jump out here and then it'll return. So it's not going to return from inside. And I'm only doing it this way to make it less confusing. Okay, so if this is equal to 0, then return 0. Otherwise, LF num is equal to 1, then return 1. What if I just do this? If num equals 0 or num equals 1, then return num. How's that? That's pretty clever. All right. Otherwise, else. Otherwise, I want to compute F. Fib equals compute nth fib of num minus 1 plus compute nth fib num minus 2. Okay, so if this is 3, then this, no, let's say this is 2. If this is 2, then this is going to be compute the Fibonacci, compute where n equals 1. So this is going to be, if this is 2, then when this executes, this is going to be 1, and it's going to hit this base case. And then this is going to equal 0. This is 2. This is going to equal 1, and this is going to equal 0. And those are the two base cases. So each time it's going to return whatever it is, and so this is going to return 1. This is going to return 0. 0 plus 1 is 1, and then we can return that 1. So we can actually, okay, no, not return. Remember, I'm using a variable called ret, and this is where I return ret. Okay, so the only reason I'm now, you know, I could put the return statement here, I could put the return statement here, but just to make it more clear and understanding, where when this method starts executing, it's always going to end right here. In this if case, once this is executed, it's going to come down to here and execute the return. In the else case, once this is executed, in fact, I'm just going to, of course, once this is executed, then I come down here. And then also notice that once this is executed and this is executed, then nothing else happens. It just returns. Everything that happens is actually it's just right here where once these start returning, once these methods start returning their values, then it adds up. Okay, so now I'm going to, in this case, I think I actually had it. I was gonna see what it looks like when we put in those indents, you know, those indents to in those print statements. So what I'm gonna do is I'm going to create an indent. I'm going to say indent. This is going to be indent. And this is going to be indent. And, oh, no, so this is the first, oops, no. So this is the first time it's called. I have a new parameter there called indent, but the first time it's called, I'm just going to put 3 spaces there. And then when these are called, I'm going to put indent plus space, space, space. And here's going to be indent plus space, space, space. Okay. And I'm going to print right here. Oops. I'm going to print indent, and I'm going to say num equals num. So I'm going to incoming num equals num. How's that? And then here I'm going to say, I'll tell you what, I'm going to do this instead. I'm going to take this and I'm going to say F1 equals that. And I'm going to say F2 equals that. And I'm going to say return F. I'm going to say R equals F1 plus F2. I'm kind of getting carried away here. I know. Return R. Because I want to see what these look like. Okay, so what I'm going to do now is I'm going to do print indent, comma, and I'm just going to say F1, comma, F2 equals F1, F2, comma, and I'm going to say returning R. Okay, so I'm kind of getting carried away here, but basically I'm going to print out all these things with this thing indented there like that. So I'm going to save this and I'm going to run this. See, earlier today, I was trying to write this program and I wasn't getting it. I couldn't get it to work. So then I went back and I added these indent things. So the trouble with when I'm doing it now is I think what I've typed in here is the correct answer, and so it's too bad I didn't record what I did before because I was doing something wrong. I don't think I had this right. I didn't have this right. I didn't have this right, and I didn't know what was going on. But anyway, so let's see what this looks like. I'm going to save this, and I'm going to run it, and I'm going to do my Python interpreter, Python 3.9 is that. Let me get out of here. Control C, Control V, exit. All right, CLS. All right, Python test.py. And okay, so okay, so the first print statement is going to be this. Let's put this over here. The first print statement is going to be when this thing first comes in and num equals 4. So n equals 4, so it's called with 4 and then 3 spaces. So first incoming is 4, and then it comes down here, and it's going to do the else case because num is 0 to 1. And then, so the first thing it does is it does this. It executes that. And so that's going to come back in here again. And that's this one. That is this one. Where this is going to be 3. And then it comes down again, it executes the same thing again, and it's going to be with 2. You know, I'm going to put a little asterisk like right here, just to keep them separate. Okay, I'm going to throw in a little asterisk right there. Let's run this again. All right. Okay, that's a little bit more revealing. So this is 4, 3, 2, 1. That's going to be this call. This is going to be called at 4. This is called at 4. Comes in and prints at 4. This is going to print 4. This is going to print 3. This is going to print 2. It's going to print 1. It's all this one. So all those are called dint, 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 dint. And then because once we get down to 1, then that's this path here, this path, 4, 3, 2, 1. Then this thing hits, and this return value gets set, and then this is done. So it jumps down to here, and it returns. And so this return, this finally is done. That's this one. This incoming equals 1. Once this is done, it's gonna this is gonna return a 1, and then we can execute this one. We're down at num minus 1 is equal to, it's 2 minus 1 is 1. So here, the first one is going to be 2 minus 1 is 1. And then once that's done, then this is going to execute, and that's 2 minus 2, and that's 0. So that's why this next one here that's this one. The indent has got a little asterisk in the middle. So that's the 1. So when this comes in, it's 1, and that's got an asterisk in it. So so when we're down at num is equal to 1, we come in and num is equal to 1. Then this executes. No. Num is equal to 1, so this executes. This is done. Then this executes, which is going to be num is equal to 0. Then finally, once num is equal to 0 is done executing, that's this one. Then we do this, and then we're able to print this out because we finally made it down to here. And so we print and which indent is that? It is the first indent from. No, it's right. It's the return from this. And this is the first return we're doing, so it's got to be a return from this one, the first one, and so that's why there's no no asterisk there. And this is incoming equals 1 from num equals 2. It's, we see a 1 and a 0 with an asterisk. Then we see a 2 and a 1 where the second one's an asterisk. Then we see a 3 and a 2 where the second one is an asterisk. And then we see a 4 and a, I don't know where the 3 is. Must be this returning the 3. So anyway, and then it finally returns the 3, which is this thing, and then it just prints out what was returned. So this will continue to work. We can. It's too bad I should have done this with a. Or I actually had an error in this, so we could see it trace through. Maybe I'll do that next. Sometime in the future, I'll do that. Okay, so anyway, that's a good explanation of that. I didn't get a chance to. It's 11:30 already. So I'll tell you what, let me just, let me take these print statements out. What am I supposed to enter here? Here. Oh, I'm just supposed to enter this. Oh, without the indent. Oh no, it doesn't. It won't have the indent. Okay, so it's this. So this isn't actually oh. Oh, why do I have these here? Oh, no reason. The next algorithm that this section discusses is the greatest common divisor problem, and I thought this was a pretty important algorithm to go over because you're going to see a lot of it in the future. Okay, the greatest common divisor is the GCD, or the greatest common divisor, is the largest number that divides evenly into two numbers. Like 12 and 8, for example, the largest number that divides into these two numbers is 4. The algorithm to compute the greatest common divisor subtracts the smaller number from the larger number until both numbers are equal. Okay, so it and it works. Some famous mathematician, Euclid or somebody, came up with this, but oh, it's Euclid in 300 BC. Okay, so so that's this is a real easy program to write, and it's another one of these where you can write it iteratively, or you can write it as a recursive program. And so if we look at it here, here's an implementation of it. We read in two numbers, and the first thing it does is it checks to make sure that they're both greater than 1, because they have to book, because neither value is below. Okay, and then it calls the recursive program GCD on the two numbers, and GCD, my GCD, continually does this, subtracts the larger from the smaller as they come in until the two are equal, and at that point you have the number, you have the greatest common divisor. So here's the function. It's the two numbers come in, and first thing it does is it takes the mod of one and the other, and if it's 0, if the result is 0, if n2 evenly divides n1, then you have the number, and so you simply return that. Otherwise, you take the smaller number and pass it in as the larger number, and then you take the result of n1 mod n2, if it's not 0, and that's passed down as the smaller number. And so the terminating condition is, the two are equal, and if the smallest that it's going to be is 1. So anyway, so that's a pretty important algorithm. Here we talk about the depth of the recursion, and you know, that's how nested down it goes. And what that is, because each call consumes memory, and so it's not like an iterative program where as the thing iterates, it doesn't consume any more memory. All right, so I think I'm going to skip this. Okay, what's next? All right, let's go straight to. Let's go straight to the labs, to the lab programs. Oh, I just wanted to mention. Okay, so if you get into, like, you know, if you decide you're gonna become a software engineer and you're gonna write algorithms to sequence DNA, or you're gonna write gaming programs, which you know, you want to explore all the possibilities, you know, far into the future, and find the best path. Maybe you're trying to find a particular outcome. Those sorts of programs usually use some sort of tree as its basic algebra, as its basic data structure, a tree of all possibilities, for example. And to traverse the tree is best expressed as a recursive algorithm, because it's like a tree. It's like, in this case, a tree is probably defined as having 3 children, and each child is a tree. And so that's the definition. And the thing can be as deep as you want, because each tree, the definition is that its children are trees. And so so as you're traversing the tree, you can just call yourself on your children. And you know, there's got to be some terminating condition, like there's no more children, and then you start, you know, returning, and so on. And then there's the different ways you can traverse the trees. You can go this way and go down first, or, you know, and so on. And you've probably seen that: depth first, you know, breadth first, and so on. And here's a bunch of examples of other algorithms that are used in, like, networking and find the distance of traveling 3 cities, and these are all algorithms that are nicely expressed recursively. All right, so let's do lab 14-7, all permutations of names. Okay, write a program that lists all ways people can line up for a photo. The program will read a list of one-word names and then use a recursive method to create and output all possible orderings of those names, 1 ordering per line. So, so for example, if the input is Julia, Lucas, Mia, these are the different combinations that Julia, Lucas, and Mia can stand in line, and we're supposed to write a recursive program to generate this. Okay, so I suspect it's okay. So the recursion is probably going to be Julia, and then you call yourself called again. It's going to pull off. Okay, so you have a list. You're going to. Okay. Anyway, let's see how this. Okay, let's see what they want us to do here. All permutations. First, you want to implement the method to create and output all permutations of a list of names. Okay, so we read in a list of names, we split them, and we're going to put the result in perm list, or perm list is going to be a temporary location, I guess. That's going to be the final list. That's going to be this. Okay. So I think the approach is going to be, first of all, we're going to figure out the size. Okay, so this is the list that's coming in, and it's going to start with this, because the first time we call all permutations, it's on the list that we're building is empty, and this is the newly split list that was just entered in. All right, so this comes in, and I'm going to, first of all, I'm going to figure out the size of it. Size equals the length of name list. And if the size is 0, okay, so the recursion is going to be, each time I call this thing, the name list is going to be smaller. Perm list is going to have stuff in it, I think. How does perm list get? Well, anyway, we'll see. Okay, so if the size is equal to 0, then this didn't have any names left in them, and we're going to print out. Okay, then we're done. So let's print out perm list. So how do we do that? For I in the range of the length of perm list. We're going to print perm list I of I. And we're going to keep on, or we aren't going to print a line feed. We're just going to print a space in between. And when we're all done printing that line, then we'll print the line feed. Okay. If the size is not equal to 0, then this is the recursive part. So else for, is this all the combinations? Or the permutations? Okay. For I in the range of size, size is this, so it's the length of that. So for all of the names in the name list that we've been given us, we're gonna create this. We're gonna create a new perm list, and we're gonna create a new name list. And so to pass to the, we're gonna have a all permutations new perms and new names. And so what we want to do is create with this new perms is going to be a copy of perm list. And it's because these are lists and they're mutable, which is why we have to make a copy or some reason like that. And then we want to append we're appending name list onto the end of, we're appending the name list that came in onto the end of new perms. No, we're appending the element. We're appending. Oh, one by one, we're appending these names. So in this loop, one by one, we append the name onto the new name list that we're. So how does this thing get smaller anyway? Let's see, it's names list that has to get smaller, not perms, not perm list. Perm list is storing our results as we go. So it's the new names that has to get smaller. So new names is equal to a name list, a copy of it. And we want to, what's, is the Python, oops, what happened? Sorry. Python pop a list. That returns a single element. It returns a single element because that's what we're using here. New names pop that particular element off of new names. I see. So this pops the current element. Okay, so names list comes in, and what we are passing down is we want the permutations of, or we want all the permutations of the first, the sublists, basically. So when we pass this in, we are then going to ask for all the different permutations of this, and we're going to do that by calling this function, and then this is going to call itself again and ask for all the permutations of this. Okay, and the names will be that until the size of what comes in is 0. And each time we're doing this, we're passing down a new perm list that has got the name that we've popped off, which is I. This I is, this is this. So this is a particular name that's appended onto new perm. Okay, and then a copy of it is made because we're going to pass that down, and this simply makes this simply removes the first one. The ith element of the list. This takes the ith element of the list and appends it onto new perms, and this removes the ith element of the list of the copy. So instead of the ith element now being here, it is now in there. That's basically how it happens. So I'm not. I'd like to see what this looks like. So I'm going to copy that and put that here and run it. See what. Okay, this is apparently the right answer, but I'm curious. Is there anything I can add here to help me understand what is really going on here, or show you what's really going on here? I'm gonna remove this. And I want to see what happens. Okay. This double space here is okay. So it prints out. Oh, it's printing out this loop here. Okay, I get it. Okay. Well, anyway, let's move on to the next. I'm not gonna. I don't need to say this. Oh, I never submitted to see what I got the way. Okay. Anyway, you can see if I got the right answer. All right. Let's see. Okay, I clicked the wrong button there. All right, so let's do 14.8 number pattern. Okay, in this program, we're supposed to write a recursive function called print num pattern to output the following number pattern. Given some positive integer like 12, subtract another positive integer like 3 continually until you get to 0 or past 0. And then you continually add that number back up again until the first number is reached. Okay, so for example, if you input 12 and then 3, the output is going to be subtract 3, subtract 3, subtract 3, subtract 3, and you've hit 0. So then you start. Then you go in reverse until you get back up to the number. So it's add 3 and add 3 and add 3 and add 3. Okay. So the strategy is we're going to say print 12 and then call yourself on 12 minus 3 and then print 12 again. Okay, I think that's what this. I think that'll work. Okay. So I haven't written. I've got a solution, but I haven't actually written it yet. So all right. So it's this. This is the function. This is the method we got to write. It's this, and the num1 is what we're starting with, and this is a number that we subtract till we get down to 0 or past 0, and then we add until we get back up to here again. Okay, so I'm going to write def print num pattern. Oops. And what has to come in is the big num, the target num. Well, I'm just going to write num1, num2. And num1 is this target. I'm going to call it tnum. And this is going to be what we subtract, snum. Okay, how's that? That's okay. All right. So first of all, the base case is if it's less than or equal to 0, then we just hit this thing. We just print that number out once. All right, that's the base case. So if right, that would be tnum1. tnum1 is less than or equal to 0. If that's the case, then just print tnum1 and don't do a line feed. Okay. And then after that, I guess we are done. So I'm just going to put a return here. Okay, so I could do that, or I could put an else here. I think I'm gonna do that. Okay, so I'm gonna do this by putting an else here. Else, we're gonna print. As I said before, we're gonna print just like up here. It's 12 and 3. We're going to print the 12, then we're going to call ourselves on 9. Call ourselves on 9. Okay, 9 and 3, and then we're going to call ourselves on 6 and 3 and 3, like that. Okay, so first I got to print the tnum1. And then yeah, I just got to print it all, but I don't want to print the line feed. And then I got to call myself. So I do, and I guess something's funny with my keyboard. Then I want to call myself print num pattern. That's right, I don't return it. I'm not really returning anything. So this is just a method that's called by itself. And it's going to be tnum1 minus snum2, comma, and we still got to pass in the snum2. So this snum2 stays the same all the time. Yeah, right. So we aren't really adding the second integer back again. We are just, once we get down to here, then we are going to print, we actually print it in reverse. We're actually printing it in reverse order, see? So we aren't really adding anything back. So anyway, so then we print tnum1 again. And again, we're going to do n equals. And then we return. So this print says we're going down. And then this calls, this just prints, you know, well, I think you understand it. This prints this, and then this calls itself and does that. And then when it's all done, it prints the 12, which is this. So anyway, let's see if this works. So I might as well try 12, 3. No, 3. Yeah. All right. Okay. Well, what time is it? 4:06. Actually, I think I'm going to end it here, and then next week we can start chapter 15. This chapter 15, is it's a lot more than searching and sorting. The important searching and sorting. It is it's the algorithms part. It's this O notation. It's algorithm analysis, and that's the science. That's the science of computer science. And knowing, you can have, there's like 6 or 8, famous sorting programs and sorting algorithms, and each of them has a different, well, they don't really, there's 2 classes. Half of them have an O notation of O of n squared, and the other half of them have an O notation of O of n log n, and O of n log n is better than O of n squared. So it's that kind of stuff. And when you're traversing trees, or you're trying to figure out all the possible cases, like let's say you're writing a program to play chess, and you have a tree which goes all the possible cases from the starting of the game, and you want your algorithm to be able to visit as many nodes of the tree as possible in a certain amount of time, because you don't have all day. You can't do all the possibilities. You have maybe a couple minutes or something. So that's what that's important for. So we will start that next time. But in the meantime, I finished up chapter 4 here. I mean, chapter 14, and we will be revisiting recursive algorithms in the future, in the future classes, and we will be returning to what we've learned in this chapter 14, to debug our algorithms. All right, so I will see you next time. Thanks for watching.